today's lecture is just to go back and practice a little bit of momentum conservation. So remember, what momentum conservation says is that if the net force on a system is equal to 0, therefore the momentum is conserved. In other words, P final equals P initial, or the momentum at any time is the same, right? Momentum is conserved. Let's just do a two-dimensional problem, right? We did one-dimensional problems. It really doesn't matter whether it's one-dimensional or two-dimensional. It's done exactly the same way. Let's do another sticking collision, right? Remember, it is important to understand what we talked about in class for quite a while, is that in sticking collisions, momentum is conserved, but energy is not. Mechanical energy is not conserved. I can't say it in any different way. You got to understand that you cannot conserve mechanical energy in a collision. In other words, we can't use work total equals change in kinetic energy. We can't use work equals change in mechanical energy. We can't use KE plus PE initial equals KE plus PE final for a collision, a sticking collision, or an inelastic collision. You can only use it in a bouncing elastic collision. E is conserved in an ideal bouncing or elastic collision. So if two things bounce off of each other, energy may not be conserved. It's only conserved if you're told it's an elastic collision or if you figure out that it's an elastic collision. But in general, so don't in general assume energy is conserved in a collision. Okay, so let's do another sticking collision, but let's do it in two dimensions. Let's say that we have our little car. We'll give it a mass. My mass of my car is, let's say, 500 kilograms. And let's say its velocity of the car is equal to, it's going slowly towards an intersection, 5 meters per second in the plus x direction. Let's call that the plus x direction. And now let's take a second vehicle and let's do a top view and say that this vehicle is going in, let's call it the plus y direction. And let's make this a truck. And let's say that the mass of the truck is 1,000 kilograms and velocity of the truck is equal to, let's say it's just rolling through the intersection, 3 meters per second in the y direction. Okay, I've given you some roads. This is a top view. Yeah, they're not really driving on their sides. Let's give them wheels on both sides. Top view. Wheels on both sides. There you go. So it looks, I don't know if you can tell that that's a car and a truck, top view going through an intersection. Let's say they get to the intersection and they crash into each other and they stick, right? So before the collision, they're going at the things that are written down. After the collision, right? After the collision, they crash and they stick to each other. We got to draw 8 wheels. Anyway, and they go and they slide off. And just forget about friction. We're just going to say before the collision, these are their speeds because they're driving. After the collision, immediately after the collision, what's the speed? And if there was no friction at any time after the collision, what's their speed? And what's their velocity? So they collide and stick. What is velocity immediately after collision? They stick, so we only have one velocity we have to deal with. Okay, let me tell you something right now. This problem will be on the third exam. This problem will be on the third exam. I may change the truck and the car to an ant and a bumblebee, and I may change the numbers, but this exact problem will be on the third exam. So you better learn how to do it. Okay, so what is the velocity immediately after the collision? First thing I want you to do is think about, what do you think the velocity should be? Qualitatively, approximately. In other words, what should the value be? Should it be bigger than 5 meters per second? Should it be smaller than 3 meters per second? What direction should it be in? And I'll tell you, I mean, so you can think about it. Okay, now you've thought about it. You can pause it if you want to think more. That these two vehicles, I think, are going to go off in a direction somewhere between the X and the Y direction. And probably the truck, I'm looking at it and I know a little more than you do. The truck has a little bit more momentum than the car, so it's going to sort of go off above 45 degrees. That looks like 45 degrees, but anyway, above 45 degrees. And I think that the velocity is probably going to be somewhere between 5 and 8. It's not going to be 8 because we can't add these like scalars, because this is a vector problem. But it's probably going to be somewhere between 5 and 8. But the angle that I'm interested in looking at is this one here, right? The angle from the direction of the car, from the initial direction of the car. What's that angle? So let's go ahead and conserve momentum and find out if we're right. So here you go, conservation momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. The momentum before the collision of the car, M car V car, plus the momentum before the collision of the truck, M truck V truck, equals the momentum of the mass afterwards, which is both masses with some final velocity. And what we want to do is evaluate the final velocity. It's a vector equation. If you do not treat it like a vector equation, when I give this problem on the third exam, you will lose 1/2 of the points. Okay, so let's go ahead and plug into that vector equation. So M car 500, I'm just remembering the equation from the previous diagram, from the previous page. M car, V car, it's going plus 5 meters per second. It's a vector equation, so we got to put in the vector velocity. That's the initial momentum for the car. The truck, 1,000 kilograms, times the initial velocity of the truck, which is plus 3 meters per second in the J direction. And that equals the final, the total mass, 1,500 kilograms, because they stick together, times the final velocity. And we are solving for the final velocity. So it's done. I mean, there you go. Solve for the final velocity. We can just solve, divide by 1,500, and we've got, well, I guess we can multiply these out. So we've got 5 times 500 is 2,500 kilogram meters per second divided by 1,500. So it's 25 over 15 kilogram meters per second I, plus 3,000 divided by 1,500, 2 kilogram meters per second J. That is your answer. It's not, well, here, let me do 25, 15. Okay, so it's 1.67 kilogram meters per second I plus 2 kilogram meters per second J. Okay, so then remember the units of momentum are kilogram meters per second. If we're using MKS units, these all work out. Okay, oh wait, whoops, that was a total mistake. Wish I could take it back, but I'm not recording using something I can take it back on. Okay, what was my error? Good error to make, just to point out. I wasn't paying attention to units. On the left-hand side, I've got kilograms, meters per second. On the right-hand side, I've got kilograms. I had done 2 steps where I had multiplied the 500 kilograms times the 5 meters per second and then divided by 1,500 kilograms, but I forgot to take out the kilograms. So the answer is 1.67 meters per second, which makes more sense because it's a velocity. That was the thing, is I saw, oh wait, how could a velocity be kilogram meters per second plus 2 meters per second J? So that is the answer. The final velocity is that. You say, but is that an answer? Yes. I've always said that if we have a vector, you can give me the vector components or the magnitude direction, unless I ask for the magnitude direction. So I could say, what is the magnitude and direction of the velocity? That would actually help because in the previous page, we were trying to predict the magnitude and direction, right? So really, I guess maybe I implied I want magnitude direction. So let's go ahead and write that down. Okay, so the answer is 2.6 meters per second at an angle of 50.1 degrees above the plus x direction, above the original direction of the car. Okay, so now let's look back and say, oh, what did I predict? Remember, so this is the velocity, the speed and angle or magnitude and direction of the velocity. What did I predict? Well, actually, I predicted something that was wrong. I predicted that I predicted the angle was above 45, which it is, because the truck has more momentum than the car, so it's going more up than to the right. But I predicted that the speed was going to be somewhere between 5 and 8, right? I knew it wasn't 8 because these aren't traveling the same direction, and I thought it was going to be greater than 5 because we're adding the truck's momentum to the cars. But what did I forget? Do you know what I forgot? Think about it for a second. What I forgot is that it's a collision, and in a collision, what? Energy is not conserved. Energy is lost. So when we say energy is lost, that means that some of the velocity, right, because energy in this case is all kinetic, some of that kinetic energy has to be lost, so we're going to slow down. Energy is lost in this collision, so we slow down. So it's less than 5 meters per second. Okay, so this is our answer.